Hello. Previously, we worked on Trace 3. Now we would like to work on WASP 10. Remember, we uploaded these two at the same time. And we got them from the database bank. If you remember from this link, the database link to the particular database. And then let us proceed straight. Come over here, you click. Okay, this time I'm going to be faster. Then you come over to exotic. Come over to exotic. Then now you choose whether the standard or the advanced. Like I told you before, they are just the same to me. But this one gives you more functionalities, like assuming you are using your own telescope, you have to use the advanced uh, to perform the photometry. And I can still use it even if I do not want to use this one, but I can still use it anyway for any one I have, whether I got the data from myself or from NASA. So let me choose the advanced, and I want to prove to you they are the same. And here is the exotic advanced. I would like to I have to copy it to my drive so that my work will be saving in case if something happens. Okay, I wouldn't have to start from the beginning. Then load libraries, you click on this. Sometimes you have to do it 2 times for it to work. Something is telling me that it's going to crash because I can see it has wasted a lot of time, so it's going to crash. And then we're going to do it another time, the second time. So let's hope it goes well. And here it goes, it crashed. So let's do that again, and this time it's going to work. It's almost like that. The first time it crashes, the second time it will go. It's coming. And here we go, it's connected. So connect your Google Drive, email, continue, continue, and the process will be completed. Let's see. Great. Drive successfully mounted. You may move to the next step, and you have this tick. All right, let's move to the next step. Moving over to the second step, this is load telescope images. Uh, okay, so let's click on low telescope images and enter the path. Okay, enter the path. So you come over here, you click on drive. Please click once, my drive, and we want to work on this. Okay, so let's copy the path. Then come over here, you paste it, Control V. Then you click enter. Then you can close this. Then please enter the name of your exoplanet target. So it is wasp. Wasp. Although it is not character sensitive, so and how you want to write it, wasp 10b. Then to go online to start searching for wasp 10b, search NASA exoplanet archive. Wasp 10b. Look at that. Okay, look at it. Wasp 10b is the exoplanet, and wasp 10 is the planet. The whole star. Sorry, the whole star name. Then enter the AAVS observation code. Remember, it is MMAPA. Enter secondary MMAPA, and you may move to the next step. So identifying the targets and comparison stars in the telescope. So this is the telescope. You have to now change it. Okay, you have options to choose your telescope and even to enter your own in case your telescope in case if you need to enter your telescope here. So exoplanet watch 0.4 meter. Okay, I think this is the Las Cumbres Observatory. I don't know, I'm not sure. So, but I'm going to enter micro observatory because the data that I'm working on is gotten from the micro observatory. Then enter the star. I'm going to come over here and copy this. Then paste it. Stand, then click. Although this one did not give me the options to check to inspect my images. Okay, this advanced uh, exotic did not give me the options. So, but no problems. So we begin to check. Oh, I'm beginning to see a pattern. Look at this. Look at this, and look at this too. Okay, this big star is this big star, and this one is this one. Okay, this one is this one. So now focusing on this, I think our it is something here. It is somewhere here. Okay, so focusing on this region, I'm going to activate uh, this wheel zoom because I'm using the wheel mouse. Okay, if you don't have any external mouse, you can just click on box zoom. So I will just zoom in there. So if I zoom in, I'm seeing one. Okay, okay, look at that pattern. One, two, three, four. Look at that. One, two, three, four. So that means my exoplanet, the whole star that has the exoplanet is around there. So if I project this one, the next thing I'm seeing maybe is this one here. Okay, I think it could be this one here or this one. Let's check very well. Let's check very well. Okay, so if you look very closely, there is a little star there. Okay, this is the comparison star. I think it's this one. And if you look very closely to the target star here, there's a little star there. I think it is this one. And very close to it is this one. I think this is the target star. So you place the mouse on top of it. Then you take the target star coordinates in the X and the Y axis. So this is 295 and the Y is 185. Then you now start taking your comparison stars. We have a lot of comparison stars. These two stars are bright. I think these are the two stars there. we need our comparison star because they have this number. This is the brightest values attached to them. So we're going to take their numbers. So for the first one, I'm going to have the x is 256 and the y is 169. And the other one is C2 for the comparison star 2. We have 232 and the y is 172. You may not be able to see what I'm doing here, but I'm just writing the numbers in a paper. So you are supposed to have a paper close to you. Then these other ones are also com stars. I can identify them. So I can also take the reading. Some have C3 for the x-axis is 270 and for the y-axis is 230 and C4 for this other star here. Okay, C4 is this one. I'm going to call it C4, my C4. So X is 256 and my Y is 211. So you can go on and get up to, you can get up to 10. Like I told you, the maximum is 10 and the minimum is 2. But the more they come stars, the better your light curve. Okay, we could work on the same data set, but my light curve will be more pronounced than yours because I used more comparison stars. And if you may ask, must you always have a comparison stars? The answer is 80% yes and 20% no. Most of the times, you always have comparison stars around your target stars. Okay, it will be very difficult for you to make an observation or in a region in a star field where you do not have comparison stars. So you, in most cases, you have comparison stars. But even if you do not have a comparison star, let's assuming you have a data set and there are no comparison star, you can just choose any of these. And let's assume that none of these have numbers attached to them. So you can just take them, find them and use them as comparison stars. Okay. So then you now go ahead to enter the coordinates here. So enter the coordinates. I would open a bracket. So I have in my x-axis 295, 295, and my y is 185, 185. Then you close the bracket. Then you click enter. Then another one would come out for the com stars. Now you have to be very careful so that you don't make mistakes. For the x is 256, 256, no, 256. And the y is 196, 169, sorry, 169. I've copied this out in the paper I'm holding right here. Then comma, open another one. So for the C2 you have 232, 232, and you have 172 for the y-axis, 172. Then you close it, you open it again. Then you have C3 270, 270, and then you have 230, 230, then you close it, you open it again, then you have 256, 256, then for the y-axis you have 211, and you close it with a big another parenthesis. Then you now have it, check it very well to know if everything is in the right order. Okay, I think they're in the right order, so you click on enter. Then to prompt you that you may move to the next step. So the next step is to click on run exotic to analyze telescope images, and this part normally takes a lot of time, so I'm not going to show you the whole part. Okay, would you like to comparison stars added automatically from, yeah, Okay, even if you didn't add comparison star, it will do that automatically, but it is better that you choose the comparison stars by yourself. Like I said, this part takes a lot of time, so I'm going to cut this video short and then show you the final result. And now the photometry process has completed, and let us view our light curve. And here's the light curve, very beautiful. Okay, so about 2% of the brightness of the star was blocked during the transiting of these exoplanets. And this other uh, data point that you are seeing here is from each of the images, and here it seems like some of them will remove because they are not good. Okay, so to submit it, you come over to your drive. Okay, this is the output. Click it so that we can get the data. This is the light curve. You can share it with your group member, but we're not interested in that. We are interested in this document because this is what we're going to submit. Download, then light. Okay, this is the light curve in PDF, and this is in the PNG. Then go to temp. Let's also get one of the field of view. Let's check this one if it is good. Oh, this is good, but let's check other ones to know if other ones are better than it. Okay, this is good. The first one mean the linear stretch is good. Oh, this is bad. This is bad. Linear stretch is still better than this. This is. Oh, this is very good. This is the square stretch. The square stretch is very, very good. I think that's the final. That's the final. So square stretch is good. Square stretch. I want to download the PDF of square stretch to download it. So if you come over here, you would find them. This is the two files. So let us submit. Come over to here. Submit your light curve. Yes. Then to take you out of the Google Colab environment. So we already have entered this result, so we don't need to enter them again because we are still using the same micro observatory. The whole data we are using is from the micro observatory. The report form. Then I'm going to submit the document. Submit. Then this one is the image. This is the image field of view. So then you accept, then you submit, and update successfully. All right, so assuming you want to view all your submissions so far, if you want to view them, you come over to find the report at AAVSO. They click there. Want to find all your reports, come over here, write your observation code MMPA, so MMAPA. Then if you want to specify, you can fill those ones, but if you just want all your data reductions, just click on or just fill in your observation code and click on search, and it will bring up the whole data. So this is it. This is the whole data. This is for the trace 3. This is what was 10B. So you see that observation date. This is the date this one was observed, and this was the date this one was observed. This is the observation, the primary observer. This is observation code, and so on. If you want to delete it, you can delete it. Also, if you want to view it at the uh, NASA website, you can come over here. So this is the results page. So if you read this, These results in the table below is automatically compiled from data submitted to submitted by Exoplanet Watch participants. This process is done using citizen-initiated transit information survey, enabling NASA science. Okay, that's the name. Enabling citizen, NASA science. That is Citizen. That's the program that moves the data from AAVSO to NASA website. A fully automated pipeline built upon by this pipeline framework. Okay, so it regularly scraps the AAVSO exoplanet database. Okay, so that is it. Okay, so we can scroll and continue to scroll. Find your light curve. If you have processed a light curve and uploaded it on the American Association of Variable Star Observers, then click on the name of the exoplanet you studied in the table below and search for your AAVS observation code and so on and so forth. I just checked right now and I discovered that the link to that table or even the table itself is not here. Maybe they are working on the web on their page, okay? Because sometime in the past it's developed some problems. So if you check back, maybe after watching this video, because at the moment of recording this, we can't find the table. So, but by the time you find this video and you watch this video, you might find it because they may have bring it back. So, but it is definitely here that you will find it. Definitely here that you'll find it. So that is it. One other thing I would like to talk about is this mid-transit time. If you observe, it is in Julian date, okay? And it will be very, very hard for you to understand it. So we want to convert it from the Julian date to the UTC time in our own date that we understand. And to do that, you come over to the links that I provided. You will see Julian date, calculator, and calendar. So you click there. We're going to enter those numbers there. And if you look at those numbers, there is decimal part. You don't approximate anything. So enter it the way you see there. So, okay. Okay, that's one in. That's okay. Julian date. So I'm gonna enter 24.60224.75759. So convert to UTC. And here is the time. The calendar date for this is this. So that is October 7th, 2003. And this is the timing. Some different format for your copying and pasting, please. So this is October. Okay, so these are the different year, month, day, hour, minutes, seconds. So this is it. Okay, this is the day this observation was made. I can remember I made it, and so on and so forth. So this is how to convert from Julian date to UTC. You can also do the vice versa. If you want to convert from UTC to Julian date, you can always use this link that I have indicated in our exoplanet research links. So the next one I'm going to talk about is how to acquire your own data. How to acquire your own data. So after analyzing WASP 10 and this one, I want you to go ahead to work on the other four on your own. So these are the ones I have for you. But after working on these, how do you then start to acquire your own fresh data? I mean, if you have a telescope, or maybe you have a telescope time in one certain robotic telescope, how do you start to acquire your own data? So that will be the next topic in the next training.